In section 7.3, we solve equations involving trig functions. Join me, Precalculus Online starts now. Section 7.3, solving trigonometric equations. So let's do the quick review. Answer the following questions. Let f of x equal x squared on the domain from 0 to infinity, including 0. Find f inverse, and then compute the value of f inverse of 25. So, if we have the function here, that is the semi-parabola, because it's only on the right side, then we know that the inverse is the reflection over the y equals x line. And so the inverse is f inverse of x is equal to the square root of x. And then the question is, what is f inverse of 25? Well, f inverse of 25 would be the point on the curve where x is 25, and that's the square root of 25, which is equal to 5. No problem. Example number 2. Solve for x. X squared equals 25. Well, in this case, I want to take the square root of both sides, but when I do that, I have to acknowledge that I could have used both the positive 5 or the negative 5 to get 25 when I square the x. Another way of looking at this is to move the 25 to the left side, factor both sides, and you get x minus 5, x plus 5 as the factorization. Split both of these up, you get x equals 5, and you get x equals negative 5. And we explore further. How many answers did you get for problem 1? Well, we just got the one answer. How many answers did you get for problem 2? We got 2 different answers. And number 5, explain why the number of answers for 1 and 2 are different. And then the explanation is the following. In number 1, this is a function. Underline that. Function. And can only have one answer at most. Number 2 is an equation. And when solving an equation, you must find all solutions. And that's the difference. If you are working with a function, you can only have one answer. If you are solving an equation, you find all possible solutions that match that equation. And that's the situation we're presented with today. In the previous section, we were dealing with the inverse trig functions, so they only had one answer. Today, we'll be looking at solving trigonometric equations and finding all answers. Solving trigonometric equations. What is the solution to a trigonometric equation? A solution is any value that satisfies the equation. That's actually just the general definition of a solution to any equation, not just a trigonometric equation. But if you can find any value that satisfies the equation, meaning you plug it in on the left, plug it in on the right, and you get the same thing on both the left and the right, then it's a solution to the equation. Let's see how this manifests itself with trigonometric functions and equations. So example 1, solve the equation sine of theta is equal to 1/2. Give the general formula for all solutions and then list 8 of these solutions. So the first thing is I want to find where the sine of theta would be equal to 1/2. Sine is the y coordinate, so I'm going to draw a horizontal line at y equals 1/2. And then I'm going to find these points here and here. So this angle and the angle that forms on the second quadrant would be values of the angle theta that would give me 1/2 when I take the sine of those. Well, what are those angles right here? Well, it's theta is equal to pi over 6, and theta is equal to 5 pi over 6. But we want to find all solutions, and we know that the period of sine is equal to 2 pi. So in fact, what I can do is I can take multiple rotations around the circle and end up on these points as well. So the way that we find the general formula for all solutions is we say that theta is equal to pi over 6 plus, and then we acknowledge we can add any multiple of pi over 2, because that's the period, to this pi over 6. So we say plus 2 pi k, and then, or the other solution, 5 pi over 6 plus 2 pi k, again representing the rotations. And then we need to specify what the k is, where k, and here's a math symbol, is in, it looks like a little e, but it's not. And then I'm going to use the fancy z symbol. The fancy z symbol stands for the integers, which means k can be any integer. And it could be a positive integer, negative integer, could be 0, just wipes that out. But then that allows me to have multiple complete rotations around the circle and then add it to either pi over 6 or 5 pi over 6. This representation here is the general formula for all solutions. Technically, you're supposed to include the where k is an integer for all of these. I think we'll just, at this point, acknowledge that when we write it in this form, the k does represent an integer and call it good. Now that's the first part. Then it says list 8 of these solutions. So the way we get 8 of these solutions is by picking values of k. So if k is equal to 0, 2 of the solutions that I get are pi over 6 plus 2 pi times 0. Well, the 0 wipes all that out, and I just get pi over 6. No surprise there. Same thing with 5 pi over 6. We get 2 pi times 0 is equal to 5 pi over 6. I can do another one. Running out of space here a little bit. But how about k is equal to 1? That would be pi over 6 plus 2 pi times 1 is equal to, and here you have to figure out a way of adding these fractions together. Let me show you the trick that I use. I do the denominator times whatever number is going to be here. In this case, 2 times 1 is 2. 6 times 2 is 12. And then there's a 1 in front of this one, so plus 1. So this becomes 13 pi over 6. And then also, let me do the 5 pi over 6 plus 2 pi times 1. So we get 6 times 2 is 12 plus the 5 is equal to 17. So this is equal to 17 pi over 6. You could continue, choose another value of k. Let's say k is equal to 2. So we get pi over 6 plus 2 pi times 2. Again, using my trick, this would be 6 times 4, because you get the 2 and the other 2 is 4. So 6 times 4 is 24, plus 1 is 25. So this would be 25 pi over 6. And then 5 pi over 6 plus 2 pi times 2. That would be 24 plus 5 is 29 pi over 6. And then the last one, you can actually let k equal -1, because it could be any integer. So we'll just go back a rotation. That would be pi over 6 plus 2 pi times -1. That would be 6 times -2 is -12, plus 1 is -11. So that results in -11 pi over 6. And 5 pi over 6 plus 2 pi over 2 pi times -1 would be -12 plus 5 is -7. And that's -7 pi over 6. So there's lots of ways to do this. Any value of k would work. Pretty much we stick to 0, 1, 2, and -1. So we cover the first few periods, and then we go back one period to make it all look nice. That example was one where you find the general formula and all representations of the solutions, and then 8 particular solutions by picking the value of k. Most of the problems that we do in this class, we go ahead and we restrict the domain for what theta can be, and then we just find all solutions within that domain. Simplifies the work a good deal. Let's look at example 2. 2 cosine theta minus root 3 is equal to 0. So this would be 2 cosine theta minus root 3 equals 0. Move the root 3 to the other side. Divide both sides by 2. And now we have the cosine of theta is equal to root 3 over 2. Draw the unit circle. Cosine of an angle is equal to root 3 over 2. That occurs in 2 places, here and here. And again, let me emphasize that we're not just finding the one angle by taking the inverse cosine. We have to find all angles between 0 and pi over 2 that meet this condition. So we're going to have this circle with these 2 points, here and here. So we're going to get the first angle and the second angle. And so these angles are, in fact, pi over 6 for the first one, and 11 pi over 6 for the second one. And those are the 2 solutions to this equation. Example 3, solve the equation. Sine of 3 theta is equal to negative root 2 over 2 on the domain from 0 to 2 pi. So in this case, it's a little bit different because the inside is not just theta, it's 3 theta. Anytime you have a multiple of the theta, you want to list that many periods of the function in order to solve. So what we want to do here is we want to list 3 periods to help us solve this problem. So let me draw the circle. And we're looking at sine. Sine is a y-coordinate. We're looking for where the y is equal to negative root 2 over 2. So that's here. And then let's find these points on the unit circle, the angles. That would be 5 pi over 4 and 7 pi over 4. Now, the angle that we're dealing with at this particular moment is not theta. It's 3 theta. So I'm going to list all of these that 3 theta could be. It's going to be 5 pi over 4 and 7 pi over 4. That's in the first rotation, like so. Now I need to continue on to a second rotation and a second rotation for the second angle as well. So what do we get here? Well, the easiest way is to add 2 pi to the answers you already have. So let me do that right here. Let's just say we're going to add 2 pi. to each of these answers above to get the new ones. Since we're dealing with fractions of 4, 2 pi is actually 8 pi over 4. So you want to add 8 to the numerator. 5 and 8 is 13, so that's 13 pi over 4. And 7 plus 8 is 15, so it's 15 pi over 4. That takes care of the second rotation. Add another 2 pi to the previous answers, and 8 plus 13 is 21 pi over 4, and 15 plus 8 is 23 pi over 4. So we had the first rotation answers, 5 pi over 4 and 7 pi over 4, and then we got the second rotation answers, 13 pi over 4 and 15 pi over 4, by adding 2 pi to the first rotation. To get the third rotation, we added 2 pi to the second rotation, and it all worked out very well. Now, those are not the answers. Those are the answers for solving for 3 theta is equal to these numbers. So now what we got to do is we have to solve for theta by dividing each of these by 3. So a reminder that dividing by 3 is the same as multiplying by 1/3. And essentially multiplying by 1/3 means multiplying the denominator by 3. So in the first one, it'll be 5 pi over 12. Because dividing by 3 is the same as multiplying the denominator by 3. Basically multiplying by 1/3. So we get 5 pi over 12. Next we get 13 pi over 12. The next one should be 21 pi over 12, but let's go ahead and simplify that down to 7 pi over 4. Then we have 7 pi over 12, 15 pi over 12 simplifies down to 5 pi over 4. And lastly, 23 pi over 12. And those are the 6 answers for this equation. Example 4. Solve the equation. 6 cosine of 4 theta plus 6 equals 0. So notice that the 4 theta indicates we need to list out 4 periods of solutions. So 6 cosine of 4 theta plus 6 equals 0. 6 cosine of 4 theta is equal to negative 6. Divide both sides by 6. We get cosine of 4 theta is equal to negative 1. Once you get down to the trig function of the angle is equal to a number, that's when you can look at the circle to see where the solutions should be. Cosine is the x-coordinate, so I need the x-coordinate to be equal to negative 1. That happens in one spot on the unit circle. That's a straight line right there at theta equals pi. So there's only one point on the unit circle for this one. There were 2 points on the circle for the previous one, and we had 3 periods. That's the 2 times 3 was 6. That was 6 answers. In this case, there's only 1 point. We need 4 periods, so there'll only be 4 answers. So we're solving for 4 theta. So 4 theta is equal to pi. Then we're going to add 2 pi to get 3 pi, and another 2 pi to get 5 pi, and another 2 pi to get 7 pi. So that one was no problem. Solve for theta by dividing by 4. And we get pi over 4, 3 pi over 4, 5 pi over 4 and 7 pi over 4. Example 5. Solve the equation. Tangent of theta minus pi over 6 is equal to 1 for theta between 0 and 2 pi. So in this case, let's go ahead and look at the circle. This one is sort of a shift of the circle. This one we need to split up at negative pi over 6 and then make the rotation go this way and then back around to this point here, like so. And the reason for doing that is because of the following. If we have 0 is less than or equal to theta is less than or equal to 2 pi, and I try to mimic what I have in the angle for the tangent, then I need the inside of this inequality to be theta minus pi over 6. Well, that means I need to subtract pi over 6 from both sides. And that leaves me with negative pi over 6 is less than or equal to theta minus pi over 6 is less than 11 pi over 6. And that's basically where I need to find the angle. From negative pi over 6 all the way over back to 11 pi over 6. Those represent the same point, obviously, but in terms of the interval for the angles, they are different. So now we proceed. We need to find where the tangent of an angle is equal to 1. Well, the tangent of the angle is equal to 1 in two different places. Either right here, where tangent is equal to 1, or in the third quadrant, same place, same type of angle. Oops, it's equal to 1. So those angles are pi over 4 and 5 pi over 4. So let's set that up. So theta minus pi over 6 is equal to pi over 4. And over here, theta minus pi over 6 is equal to 5 pi over 4. Solve for theta. Theta is equal to pi over 4 plus pi over 6. Get a common denominator of 12, and that would be 3 pi over 12 plus 2 pi over 12, which is 5 pi over 12. And then theta is equal to 5 pi over 4 plus pi over 6. Again, common denominator of 12. That would be 15 pi over 12 plus 2 pi over 12, which would be 17 pi over 12. And then the question is, are both of these inside the interval from negative pi over 6 to 11 pi over 6? And the answer is yes. If you're worried about this one, 17 pi over 12 is the same as 8.5 pi over 12, over 6. So it's less than 11, so we're good. Example 6. Solve the equation. 2 sine squared of theta minus 3 sine theta plus 1 equals 0 for theta between 0 and 2 pi. So in this case, let's use substitution. Let's let u be equal to the sine of theta. If I do that, then this first term here can be rewritten as 2u squared, because u is sine and we have sine squared, so that's 2u squared minus 3u plus 1 equals 0. Now we have a quadratic, and we can solve the quadratic. So how does this factor? Well, 2 is prime, so it's going to be 2u and u. 1 is just 1, so that's just 1 and 1. And then since it was plus, it needs to be the same sign on the insides, and those signs are negative. So we have 2u minus 1 and u minus 1. Verify that that is, in fact, the correct factorization of the previous quadratic. Then set each of these equal to 0. So we get 2u minus 1 equals 0, and u minus 1 equals 0. 2u is equal to 1, meaning that u is equal to 1/2, and then u is equal to 1. Next, we need to back substitute. The u was the sine of theta. So the sine of theta is equal to 1/2. That occurs when theta is equal to pi over 6 and 5 pi over 6. And we also have that the sine of theta is equal to 1, which occurs when theta is equal to pi over 2. So the three answers for this one are pi over 6, pi over 2, and 5 pi over 6. Example 7. Solve the equation. Cosine squared of theta is equal to sine squared theta for theta between 0 and 2 pi. So there's several ways to do this one. I'm going to use a trig substitution here, an identity. What do we know cosine squared is equal to? It's equal to 1 minus sine squared of theta. And the right side stays the same. And it was important to do this so that I could get all sine squareds. If you have a mixture of sine squareds and cosine squareds, it can be difficult to work with. But now they're all the same. Let me move the negative sine squared to the other side, and we get 2 sine squared theta on the right side. Divide both sides by the 2. We get 1/2 is equal to sine squared of theta. Take the square root of both sides. This is going to be plus or minus. The square root of 1 is 1, and the square root of 2 is root 2. This is equal to the sine of theta. Rationalize the denominator by multiplying by root 2 over root 2. And we get plus or minus root 2 over 2 is equal to sine of theta. So this is on the unit circle. And actually there are two different occurrences of this. Sine is y, so we want the y is equal to root 2 over 2, but we also want y is equal to the negative root 2 over 2. And so we do get these four angles. And so the answers for theta are all these pi over 4s. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Finally, let's take a look at a technology example. Solve the equation using your grapher. 0.2 x squared minus x equals the sine of x. For all solutions for, let's call that x, from 0 to 2 pi. Now the problem with this one is we have a trig function and a polynomial. In general, you can't solve those. So we rely on the grapher to do this. Go ahead and make this left one y1 and this right one y2. Be sure that you are in radians. That's the only way these make sense. And then set the windows to these values. This is the x-min and x-max with the scaling, the y-min and the y-max with scaling of 1, tick marks of 1. And then just go ahead and find the intersection points. Where they intersect for the x's are the solutions to the original equation. So clearly we have x is equal to 0 here on the left. That's the one that's showing here. This intersection down here is 4.03. We're looking for solutions for x between 0 and 2 pi, and since the x's right here covered all of that, if there are no more intersections in this window, then there are no more intersections on that interval from 0 to 2 pi.